In this lesson, we want to review applications of rational expressions, and specifically here we're going to look at some motion and some work rate problems. So at this point you should be pretty comfortable with solving word problems, and although some problems in this section will not result in linear equations, we can still rely on our little 6-step procedure that we used in our section on applications of linear equations. So again, for solving a word problem, the first thing we want to do is read the problem and determine the question or questions to be answered. Then the next thing we want to do is assign a variable to represent the unknown. And for the scenarios we're going to have today, we can express other unknowns in terms of this variable. Then the next thing we want to do is write an equation, and this is based on the scenario we're given. Then we want to solve the equation. Then we want to write the answer in terms of the question or, again, questions asked. Then lastly, we want to check the answer using the words of the problem. Just make sure that things are reasonable. So if you're in the section on applications of rational expressions, the most common problems you're going to see are going to be work rate problems, or some people call them rate of work problems, or you're going to see motion word problems, right? These involve, again, the distance formula. Distance equals rate of speed times time traveled. Okay, so we talked about this formula when we looked at applications of linear equations, so we see it again. Okay, and we'll see this throughout our course many times. So again, if you don't know the formula, d for distance is equal to r for rate times t for time. So if I'm going 40 miles per hour and I do this for 3 hours, I multiply 40 times 3, that gives me my distance of 120 miles. Okay, so this would be 120 in that case. So a pretty easy formula to understand, very, very intuitive, and we're just going to use it to kind of solve this first problem. So the Conner River has a current of 8 miles per hour. Find the speed of Lauren's boat in still water if it goes 210 miles downstream in the same time it takes to go 98 miles upstream. Okay, so what are we being asked for? We're being asked to find the speed of Lauren's boat in still water. Okay, this is what we need to find. Now we're given a lot of information to help us find this. It tells us the Conner River has a current of 8 miles per hour. It also tells us that her boat can go 210 miles downstream in the same time it takes to go 98 miles upstream. So when you get these type of problems, you need to understand the difference between still water, upstream, and downstream. Okay, so the way these problems work, if you're in still water, basically there's no current. Okay, if you're going upstream, you are fighting the current. Okay, so you have to subtract the speed of the current away from the speed of the boat in still water. If you're going downstream, the current is pushing on you. Okay, so you're going with the current, and so now you need to add the speed of the current to the speed of the boat in still water. Okay, so we'll talk about that more in a second. For right now, our next step is to what? Is to assign a variable to represent the unknown. Our unknown here is the speed of Lauren's boat in still water. So I'm just going to let x be equal to that. So let's let x be equal to the speed of Lauren's boat in still water. Okay, so that's water with no current. All right, so let's take this down to a little table so we can organize our information. So the first thing I'm going to do is put my distance formula up here. Again, d stands for distance, and this is equal to r, which stands for rate of speed, multiplied by t, which stands for time traveled. Okay, again, if I'm moving at 40 miles per hour and I do this for 3 hours, 40 times 3 is 120, so I know I would go 120 miles. Okay, it's a very intuitive formula. So I'm just going to put my two scenarios over here on the left. So we have upstream and we have downstream. Okay, so what am I told in the problem? Again, my rate in still water is unknown. That's what we're trying to find. But we expressed it as x. So I'm going to put x here and I'm going to put x here. Now, in the case where I'm going upstream, again, I'm fighting the current. The current is 8 miles per hour. So I've got to subtract 8 away from the speed of the boat in still water. So I subtract 8 away from x. In the case of going downstream, it's the opposite, right? The current's pushing on me. So I'm going to add 8, or again, the speed of the current, to the speed of the boat in still water. So for upstream, my rate is x minus 8. For downstream, my rate is x plus 8. Now, what about the distance? Well, it specifically tells us that the boat goes 210 miles downstream in the same time it takes to go 98 miles upstream. So my distance for downstream will be 210, and my distance for upstream will be 98. So for downstream, it's 210. For upstream, it's 98. Okay, so now what about the time? Well, to do the time, what we can do, we can solve the distance formula for time. So again, distance is equal to rate of speed times time traveled. Okay, so if I divide both sides by r, what's multiplying t there? We know that this would cancel with this, and I basically have that time is equal to distance over rate. So right now I have a distance and I have a rate for each scenario. So if I divide my distance by my rate, I'm going to have my time modeled. Okay, so let me erase this. So for upstream, my distance is 98 and my rate is x minus 8. So the time, again, is distance divided by rate. So it's going to be 98 divided by x minus 8. For downstream, again, my distance is 210 and my rate is x plus 8. So my time for downstream will be 210 over x plus 8. Now, it tells us in the problem, let me go back up, that the boat can go 210 miles downstream in the same time it takes to go 98 miles upstream. So all we have to do is set the two times equal to each other, because again, in the problem, it tells us that it's the same. It says in the same time, okay? So I can take 98 over x minus 8. So 98 over x minus 8. That's the time for going upstream. And set this equal to my time for going downstream, which is 210 over x plus 8. So let me just copy this. We'll go to a fresh sheet. So how can we solve this? We already know how to solve rational equations. It's very, very easy. In this particular case, I don't need to multiply both sides by the LCD, right? The LCD would be x minus 8 times x plus 8. I could multiply both sides by that, but a quicker method here would be just to cross multiply. So you take this guy right here, multiply by this. You take this guy right here, multiply by that. So essentially what I'd have is 98 times the quantity x plus 8 is equal to, you'd have 210 times the quantity x minus 8. So I could just start by using my distributive property on each side. But one thing you want to see here is that 98 and 210 are each divisible by 14, right? So to make this a little easier on myself, I'm going to divide both sides of the equation by 14. Remember, this is multiplication here. So this is legal to cancel. 98 divided by 14 is going to give me 7. So I'd put a 7 here. Then 210 divided by 14 is going to give me 15. And now I have smaller numbers to work with, so it's just going to make my life a lot easier. So 7 times x is 7x, and then plus 7 times 8 is 56. This equals 15 times x is 15x, and then minus 15 times 8 is 120. Okay, so let me scroll down a little bit, get some room going. I can subtract 15x away from each side of the equation, and I can subtract 56 away from each side of the equation. So we know that this is going to cancel, and this is going to cancel. 7x minus 15x is going to give me negative 8x. And this will be equal to negative 120 minus 56 is negative 176. If I finish this up by dividing both sides by negative 8, right, the coefficient of x there, what I'm going to get is this cancels with this. I'll have x is equal to 22. So this is what we're looking for. I can't just put x equals 22, obviously. I've got to answer my question. But x tells me the speed of Lauren's boat in still water, which is exactly what we want to know, right? So it's going to be 22 miles an hour. So I can say this is 22 here. And let me go up and just answer my question. So I can just say that Lauren's boat has a speed. Let me make this better. Of 22 miles per hour in still water. So how can we check to make sure we got the right answer? Well, again, if we go back to the fact that time is equal to distance over rate, we can just kind of think about the scenario we're given. For the downstream scenario, we know that her distance is 210 miles, and we know that her rate of speed is the speed of the boat in still water, which is 22, plus the speed of the current, which is 8, so that's going to be 30. So 210 divided by 30 would be 7. So this is her downstream scenario. It took her 7 hours to go 210 miles. Now, the other scenario, let me just set this up over here. We know that she goes 98 miles, going at a rate of speed. Remember, if it's going upstream, it's going to be 22, the speed of the boat in still water, minus 8, okay, the speed of the current, which is going to be 14. Okay, so this is 14, and we know that 98 divided by 14 is 7. So this is true, right? It took her the same amount of time to go 210 miles downstream, right, 7 hours, that it takes to go 98 miles upstream, again, 7 hours. So our answer here is correct. Again, we can say that Lauren's boat has a speed of 22 miles per hour in still water. All right, now let's move on and talk about rate of work problems, otherwise known as work rate problems. So essentially, these are very easy problems to solve once you understand how to kind of set them up. And they just deal with the rate of speed at which a job can be completed, given the individual work rates from the people performing the job. Okay, so again, very, very easy. If you understand the distance formula that we just used in the last problem, then you could understand this formula I'm going to give you here today. So the distance formula, again, is d for distance is equal to the rate of speed, r, times t for time travel. Okay, very intuitive. Again, if I go 40 miles per hour for 3 hours, 40 times 3 is what? It's 120. So I know I've gone 120 miles. Okay, very intuitive, very easy to understand. The same thing goes when we work with work rate problems or rate of work problems. So instead of D, you have A, which stands for the amount of work completed. And we think about this in terms of jobs completed. So it could be 1 jobs completed in pretty much every scenario that I've seen. But if you wanted to extend that and say, okay, we have 2 jobs completed, 11 jobs completed, 2 million jobs completed, whatever that is, okay? But A here stands for the amount of work completed. This is equal to R, which is your rate at which the work is done, okay? Otherwise known as a work rate. That's how these problems get their name, okay? Then times T, which is our time, and that's the amount of time that you're working for. So let's say, for example, my rate of work, and this will make more sense when I explain in a minute, is 1/4, okay? And I multiply this by a time of 8. What does that give me? We know that 8 times 1/4 is 2. So what does this mean? My work rate tells me how much of the job I can complete in 1 unit of time. So let's say, as an example, I'm working with hours, and let's say I was painting a house. So it takes me 4 hours to paint the house. Well, in 1 hour or 1 unit of time, I'm done with 1/4 of that job. If I work at this rate for 8 hours, okay, I continue at 8 hours, I'm going to paint 2 houses, right? Okay, that's all that's saying. If I change this to 4, then this just becomes 1, right? So if I work at a work rate of 1/4 of the job per hour, and I do this for 4 hours, well, then I've got 1 completed job. Now, in almost every case, or in every case that I've ever seen, A is going to be 1. So basically what you want to focus on here, and let me erase this, we don't need this information anymore. This R here is your rate of work or your work rate. That's what you're focused on in the problem. So I'm going to divide both sides of the equation by T. That's what's multiplying R. So I can isolate, and I'll say that R, my work rate or rate of work, is equal to 1/T. So this is very important. You probably want to write that down in your notes if you're taking notes. This is what we're going to use in almost every scenario to get an answer, okay? So you've got to know that if you're working on a problem like this and you want your work rate, just take a 1 and divide it by the amount of time it takes to complete the job. So again, in the case where we could paint the house in 4 hours, well, I would get a work rate. My R would be equal to 1/, takes 4 hours to complete it, so 1/4. And all this is telling me is that in 1 unit of time, or 1 hour, I've completed 1/4 of the job, okay? As another example, suppose it takes me 15 minutes to wash my car, okay? In 1 unit of time, which is now 1 minute, because we're working with minutes, then I've done 1/, again, it took me 15 minutes to complete it, so 1/15, or 1/15 of that job is completed, okay? So that's the general idea behind these problems. And now let's kind of jump in and look at one. All right, so working alone, it takes Heather 30 minutes to wash the car. Jacob can wash the same car in 45 minutes. How long would it take Jacob and Heather to wash the car if they work together? All right, so the first thing I'm going to do here, just like we always do, is just find out what are they asking us to find. Well, the question we need to answer here is how long would it take Jacob and Heather to wash the car if they work together? This is a pretty typical scenario. So you have their individual rates of work, right? We know that Heather takes 30 minutes to wash the car. We know that Jacob takes 45 minutes to wash the car. But hey, if they work together at the same speed that they're working at when they do it individually, how long would it take for them to wash the car? Okay, so that's what we're trying to figure out. So what I'm going to do is I'm going to let a variable like x be equal to that. So I'm going to go to the next page, and I'm just going to say that we're going to let x be equal to the amount of time. And I'm just going to say to complete the job. To complete the job. Right? But if you wanted to be more detailed, you could say the amount of time to complete the job when Jacob and Heather work together. Okay? And of course, since we're working with minutes here, the units are going to be minutes. Okay? So you got to make sure of that, because in some of these problems, you have crossovers between minutes and hours. You could have minutes and seconds, so on and so forth. But for this one, it's very easy. We're just working with minutes. All right, so let's go down to a little table. And we're going to organize some information. And then once you see this, in the next few problems, you're going to go right through it. Okay, very, very simple. So, of course, we have Jacob and we have Heather. Now, the first thing I'm going to write is the rate of work. So, the rate of work. And before we started this problem, we talked about how to get it. It's 1 over the amount of time they take to complete the job. So I'm going to put a 1 over and then blank for each one. Let's go back up. So for Heather, it takes 30 minutes to wash the car. So her rate of work would be 1 over 30. Again, for every minute that passes, she's done 1/30th of that job. For Jacob, his is going to be what? It takes him 45 minutes to wash the car, so it's going to be 1 over 45. Every minute that passes, he's going to be done with 1 over 45, or 1/45th of that job. So let's go down. Again, for Jacob, he's got a work rate of 1 over 45. For Heather, she's got a work rate of 1 over 30. Okay, so now I'm going to put time working together. So time working and then together. Now, we modeled this on the page up as x, the amount of time to complete the job. Again, this is working together. So I'm just going to put this as x here and x here. Okay, it's the same in each case. Now, the next thing you need is the total contribution of each person. How much of the car does Jacob get done in this amount of time? How much of the car does Heather get done in this amount of time? So I'm just going to write this as total contribution. Okay, so to get this, we can just multiply, right? Because if you want to know the amount of work that Jacob performed, I just multiply my R times my T, right? My A, the amount of work that's performed, is R, the rate of work, times T, the time that you're doing that work for. Well, I've got my rate of work. I've got my time that I'm working for. So my contribution here, or the amount of work that's being performed for Jacob, is 1 over 45 times x. You could write it as 1 over 45 times x, or you could write it as x over 45, which is probably a little better. Same thing goes for Heather. It's going to be x over 30, right? Just multiply across. Very, very easy. And now what we need to understand is that between Jacob and Heather, they're going to complete one job, okay? So the equation here is very easy to set up. Jacob's contribution, which is x over 45, plus Heather's contribution, which is x over 30, is going to be equal to 1. Again, that's for one completed job. So the first time you see this, it might not make a whole lot of sense. But again, after you solve like 2 or 3 of these, you're going to find that these are the easiest problems in the world to solve. So let's copy this. So what I'm going to do to clear these denominators, I'm going to multiply both sides of the equation by the LCD. The LCD, if I look at the denominators, I got 45 and 30, it's going to be 90. So I'm going to use my distributive property here. 90 times x over 45. 90 divided by 45 is 2. 2 times x is 2x. Then plus 90 divided by 30 is going to be 3. Then times x is 3x. And this equals 90. Sum on the left, so 2x plus 3x. If I combine like terms there, I get 5x. This equals 90. Divide both sides of the equation by 5. And we're going to find that x is going to be equal to 18. So 18 is the number of minutes that they each have to work when they're working together to complete the job, right? So if we go back up, again, we said amount of time to complete the job. That's when they're working together. And of course, this is in minutes. So let me just say that they work for 18 minutes to complete the job. Okay. You can answer a whole lot of different ways there. That's just a very simple sentence to say they work for 18 minutes to complete the job. Now, is it correct? How can we check this? Well, we can take the fractional amount that Heather does and the fractional amount that Jacob does and add those together and see if it equals 1. So we know that if we go back down, A is equal to R times T. I'm going to put two scenarios. A equals R times T. So how much or what amount of the job does Heather do? Well, remember her R, her rate of work is 1 over 30. And she works for T minutes. And again, we found that the time that they're going to work together, which we labeled as X, was going to be 18. So essentially I'm going to put this as times 18. That's going to give me the amount of work that she does. So between 18 and 30, I have a common factor of 6. So if I divide 18 by 6, I get 3. If I divide 30 by 6, I get 5. So I get 3/5 there. So this is going to be 3/5. That's the amount of work that she completes. Now, for Jacob, he's a little bit slower. So his rate of work is 1 over 45. And the time is the same, right? Because they work the same amount of time when they're working together. So this is 18. Each here is divisible by 9. 45 divided by 9 would be 5. 18 divided by 9 would be 2. So this is 2/5. Now, if you go ahead and take the amount of work that Jacob completes, which is 2/5, that's what he does in 18 minutes, and you add that to the amount of work that Heather completes, she's got 3/5 of the job that's completed, right? That's what she does in 18 minutes. You do get 1, right? 2/5 plus 3/5 is 5/5. 5/5 is 1. So we can say our answer here is correct. They work for 18 minutes to complete the job. All right, very easy overall. Let's take a look at another one. So working together, James and Nathan can mow a yard in 24 minutes. When James mows the yard by himself, he takes 4 times longer than Nathan. How long would it take for each person to mow the yard if they were working alone? So in the last problem, we knew their individual rates of work, right? We knew that for Jacob, he could wash the car in 45 minutes. For Heather, she could wash the car in 30 minutes. But we didn't know, or we could say we had to find how long it would take if they worked together. In this case, we know how long it takes when they work together, right? It tells us right here it's 24 minutes. But we don't know how long it takes them individually, okay? So that's the question here. How long would it take for each person to mow the yard if they were working alone? So how long does it take for James? How long does it take for Nathan? So we're specifically told that James takes 4 times longer than Nathan. So let's let X be equal to the amount of time it takes for Nathan to mow the yard by himself. So the time for Nathan, and I'm not going to write the rest. You can write the rest if you want, but it's just the time for Nathan to, again, mow the yard by himself. So then because James takes 4 times longer, again, it tells us that right here, when James mows the yard by himself, he takes 4 times longer than Nathan. What I can do is just multiply 4 times X to get the time for James. So I could say then 4X is equal to the time for James. Okay, let's go back to our table and kind of organize. So again, we have Nathan and James. So we have Nathan and we have James. And again, we have the rate of work, and we have the time working together. And then we have their total contribution. So for the rate of work, remember, it's 1 over the amount of time it takes for that person to complete the job. So if it takes me 4 hours to paint a house, again, the rate of work is 1 over 4. That's how much I'm going to do in 1 unit of time. So in an hour, I'm going to do 1/4 of the job. Here, we know for Nathan, this is in terms of minutes, he can complete 1 over X amount of that job every minute, okay? So for James, it's going to be 1 over 4X every minute. So for Nathan, it's 1 over X. For James, it's 1 over 4X. The time working together. It tells us that in the problem. It tells us specifically that James and Nathan can mow a yard in 24 minutes. That's, again, when they're working together. So each person is going to work for 24 minutes in this scenario. So what's their contribution? Again, you just multiply. This is the rate of work. This is the time working. So 24 times 1 over X. You can do just 24 over X to make it simpler. And then here it's 24 over 4X, which we could simplify. 24 over 4 is 6. So I could just say this is 6 over X. Now, How do we get an equation going? Well, we know that when we sum the amount of work done from both of them over this, again, 24-minute period, they've completed one job. So the amount of work that Nathan does is 24 over x. The amount of work that James does is 6 over x. If I add these two amounts together, I should get one completed job. So let's copy this. All right, so what can I do here? Well, I can multiply both sides of the equation by x, right? That would be the LCD. So I'll multiply this by x, and this by x. So essentially, this is going to cancel, this is going to cancel. You'll basically just have what? 24 plus 6, which is 30, is equal to x. So that's really a piece of cake. We've immediately found that x is 30, and we know that x was the time for Nathan. So this is going to be 30 minutes. And then for James, it's going to be 4 times that, or 120 minutes. If you wanted to put that in terms of hours, you could. That's 2 hours. If you didn't know that, it's okay. You can put it in terms of minutes, right? It doesn't matter. So I'm just going to say that Nathan can mow the yard in 30 minutes. So Nathan can mow the yard in 30 minutes. And then I'll say while James can do it, and you can say 2 hours or 120 minutes. I'll just say 120 minutes because the problem was given in minutes. But again, you can put 2 hours. It's the same thing. So does this make sense? Let's kind of scooch up just a little bit. So again, working together, James and Nathan can mow a yard in 24 minutes. So we know that. When James mows the yard by himself, he takes 4 times longer than Nathan. So according to our answer, James does it in 120 minutes and Nathan does it in 30 minutes. So if this is correct, we're good to go, right? Because it is 4 times. 30 times 4 will give me 120. So that part does check out. We just need to make sure that they can work together and get it in 24 minutes. So again, think about this. The amount of work that Nathan does is he's going to do 1 over 30 of that job every minute. So he's going to do this, again, if they work together for 24 minutes. And then if I add to this how much James does. So he's going to do 1 over 120 of that job for every minute, and he's going to do that for 24 minutes. If I sum these amounts, I should get 1. This is the amount that Nathan does all the way to the left. Then we have plus. Again, we have the amount that kind of James does over here. Again, if I sum them, I should get 1. So how can I reduce this here? Well, I can divide both by 6. That would give me a 4 here and a 5 here. For this one, 120 divided by 24 is 5. So I can cancel this with this and put a 5 here. So you've got 4/5 of the job, which is what Nathan's going to do, plus 1/5 of the job, which is what James is going to do. You sum those two amounts together, you get 5/5 or 1, again, for one completed job. So our answer here is correct. Nathan can mow the yard in 30 minutes, while James can do it in 120 minutes, or again, 2 hours. Okay, so pretty easy overall. Let's look at one that's a little bit more challenging, but again, it's not so much because these problems are really easy. So Claire's empty swimming pool can be completely filled from a garden hose in 30 hours. Her outlet pipe can completely drain a full pool in 120 hours. If for some reason both the garden hose and the outlet pipe are turned on at the same time, how long would it take to completely fill Claire's empty pool? So the question we need to answer here is, how long would it take to completely fill Claire's empty pool? Given these two competing forces, you've got one kind of hose pipe that's filling the pool, and then you've got an outlet pipe, or you could say a drain pipe, that's emptying the pool. So they're kind of working against each other. You can think about this as if you're filling your kitchen sink, okay, and you got the water on full blast, but you hold the stopper just up just a little bit, right? So some of the water can drain. So if the amount of water coming in is more than the amount of water going out, eventually you're going to fill your sink, right? But it's just going to take longer than if you had the sink kind of all the way stopped up, okay? So that's the idea of what's going on here. So how can we model this? Let's just say we're going to let x be equal to the amount of time it would take to completely fill Claire's empty pool. So I'm just going to say let x be equal to the amount of time to fill the pool, okay? Let's go down to the kind of table. Let's organize some stuff. So we've got our hose that's filling the pool, and then we've got our outlet pipe that's trying to drain it. And let me be more specific here and just put garden hose. So garden hose, because that's what it says in the problem. Now, again, we're going to have our rate of work. We're going to have our time working together. And then we're going to have our total contribution. So we know one thing so far, it's the time working together is x, because we just let a variable represent that. So this is x and this is x. The rate of work, let's go back up. We've got to find the garden hose and the outlet pipe. So the garden hose can fill the pool in 30 hours. So every hour it's done 1 over 30 of that job. So the rate of work is 1 over 30. So I'll put 1 over 30. Now, the outlet pipe, which is trying to drain the pool, that's its goal, okay? So every hour, since it takes 120 hours to do this, it's done 1 over 120 of that. So I'll put 1 over 120. So that's the rate of work. Now, the contribution works a little bit differently here because they're competing forces, right? You can kind of think about the garden hose as filling it. So I'm going to put a positive 1 over 30 times x, or you can just put x over 30. Really, you can think about the outlet pipe as fighting against this, right? You can think about what it's doing as subtracting away. So you can put this as a minus x times 1 over 120, which would be x over 120. So if you sum these two amounts together, you should set it equal to 1 and solve that equation. So I would have x over 30. I'll just put minus, or you can put plus, negative, doesn't matter. I'll put minus x over 120. I'll set that equal to 1. So in other words, the total contribution, or the total amount of water that goes in from the garden hose, minus the total contribution, or the total amount of water that gets pulled out from the outlet pipe, when that's set equal to 1, the value for x is going to tell me the amount of time it takes for them to complete that job, again, working together. So let me copy this. So what I want to do is just multiply both sides by the LCD, which is going to be 120. Pretty easy to do. So I know that I'm going to distribute this to each term inside the parentheses. 120 divided by 30 is 4, right? So I'd have 4x minus 120 divided by 120 is 1. So I just have x there. This equals 120. 4x minus x is 3x. This equals 120. Divide both sides of the equation by 3. And you're going to find that x is equal to 40. So that tells us what? It tells us that the garden hose and the outlet pipe can both be left on, and the pool is going to go from completely empty to completely full in 40 hours. Let's go back up. So it would take 40 hours to fill the pool. Okay, so let's check this. So again, I go back to my formula of A equals R times T. So think about this for each scenario. You have another one over here. So what I'm going to do is I'm going to say the garden hose, how much water does it put in? So we think about the rate. Again, it does a full job in 30 hours. So the rate is 1 over 30. When they work together, again, they're going to work for 40 hours. So the amount that's going to be done is what? I can divide both of these by 10. This will be 3, and this will be 4. So it's going to be 4/3 that's going to be completed. So 4/3 of the job is completed. Now I'm subtracting away what gets completed by the outlet pipe. What's going to get drained away here? So the rate there, again, it accomplishes the whole thing in 120 hours. So it's 1 over 120. And then the time, again, it's going to go for 40 hours. So 120 divided by 40 is 3. So this would be a 3, and this would be a 1. So basically, this is 1/3. So does this make sense? Yes, it does. If the garden hose completes 4/3 of the job in 40 hours, and the outlet pipe completes 1/3 of the job in 40 hours, well, 4/3 minus 1/3 gives me 3/3 or 1. Again, what's happening here is the garden hose is filling a pool and then another third of a pool. okay? So 4/3. Then the outlet pipe is taking a third away, right? It's taking that extra third away, so you're left with 3/3 or just one full pool, okay? So we can say our answer here is correct. It would take 40 hours to fill the pool.